Welcome to the deep dive. You know, there's this buzz everywhere, right? Quantum computing.
Mm-hmm.
It feels like it suddenly jumped out of these really obscure physics labs, and it's landed right in our news feeds, our tech headlines.
Absolutely. It's reshaping conversations about everything from, data security all the way to discovering new medicines.
Exactly. But let's be honest, for a lot of us, myself included sometimes, it can still feel, well, pretty impenetrable, like a whole different language spoken by incredibly smart people.
It can definitely seem that way. There's a lot of complex physics involved, naturally.
So today we're going to try and cut through all that noise, all that complexity.
Yeah, our mission for this deep dive is really to equip you, our listener, especially if you're maybe encountering this for the first time in depth, with a solid foundational understanding. What is quantum computation, really?
Right.
We want to demystify some of those, frankly, mind-bending concepts, show you the potential, the revolutionary potential it has across different fields.
And also be real about the challenges, right? It's not all magic yet.
Yeah, definitely not. We need to lay bare the very real, very tangible hurdles this technology faces as it, grows up.
And the best part, you absolutely do not need a PhD in physics to follow along today. That's not the goal here.
No, not at all.
We're not trying to turn you into a quantum physicist by the end of this conversation. Promise.
No. It's more about giving you a clear-eyed, well-informed perspective so you can genuinely understand what's going on in this field that really is poised to redefine what's computationally possible.
And just so you know where we're coming from, we've dug into some really interesting sources for this. There's a comprehensive survey looking at quantum computing's applicability, especially in areas like finance, which is fascinating.
Mm-hmm. That's a key area.
And we've also combined that with some more accessible practical guides, the kind designed to actually introduce you to quantum programming concepts.
Right, trying to get that blend of the big picture overview and the essential foundational ideas.
All crafted just for you, our listener. Think of this as your genuine shortcut, maybe, to getting properly informed about the quantum revolution without getting totally bogged down in the jargon.
Exactly. Let's dive in.
Okay, so,
Mm-hmm.
Part 1. The quantum leap. We need to understand where we're leaping from, right? To appreciate quantum, we got to quickly touch base with classical computing.
That's the perfect starting point because virtually every computer you interact with today, your phone, your laptop, the massive supercomputers running weather models, even, like you said, the chip in your smart toothbrush.
Yeah.
They all operate using the same fundamental unit of information, the classical bit.
The bit, zeros and ones, we hear that all the time.
Precisely. And it's useful to visualize what that really means. Think of a simple light switch. It's either on or it's off. There's no in between.
Okay, definite state.
Or an old school padlock. It's either locked or unlocked. Again, two distinct definite states. In the digital world, we represent these as a 0 or a 1.
Binary. True or false. Locked or unlocked. On or off.
Exactly. These aren't fuzzy concepts. They are fundamentally binary choices. And every single calculation, every operation, every piece of data processed in a classical computer boils down to manipulating these definite 0 or 1 states in a perfectly predictable sequential way.
And we see that predictability everywhere, don't we? Like, filling out your taxes online, it's just a list of instructions, isn't it?
Yep. Step by step.
Put this number here, check this box if this condition is true, or map directions, go straight, turn left, it's all sequential.
Even a simple recipe. Add flour, then add eggs, then add sugar.
Right. You can't really add the sugar before the flour and expect the same result.
Not usually, no. Each step translates into these clear, definite binary instructions. A classical computer just follows them precisely, one step after another. Definite states, definite transitions.
Okay, got it. Classical bits. Definite, predictable, 0 or 1. Now, let's make that leap. Quantum computers. They don't use bits.
Correct. This is where things get fundamentally different. Quantum computers operate using quantum bits, or as everyone calls them, qubits.
Qubits. Okay.
And a qubit. Well, it isn't restricted to being just a 0 or just a 1. That's the crucial first point.
So what is it then, if not just 0 or 1?
At its core, a qubit is any physical system that has two distinct quantum states, or two levels. So in that sense, it's analogous to a classical bit having two states. But here's the kicker. Its actual state, how it exists at any given moment before we measure it, is described mathematically by a vector of numbers. And it can be manipulated by special quantum operations in ways that classical bits simply cannot.
A vector of numbers. Okay, hold on. That already sounds way more complex than just on or off. a set of values, not just one. Can you help us visualize that?
Yeah, it's a shift in thinking. Physicists use a special notation, Dirac's bracket notation, which looks like 0 and 1 error. These symbols, the ket 0 and ket 1, are kind of the quantum equivalents of the classical 0 and 1.
Okay, so they represent the two basic states, like North Pole and South Pole.
Exactly. Think of them as ideal basis states. Maybe like the spin up and spin down of an electron or two specific energy levels in an atom. But, and this is really important, these are just the anchors. The actual state of a qubit before measurement isn't necessarily just one of these.
Right.
The real state is a mathematical model, this vector, that lets us predict the probability of finding the qubit in the zero-fifth, or the winner state, if we were to measure it.
So you can't just peek. You can't just look at the qubit and see its vector directly.
No, you absolutely cannot. The moment you try to measure it directly to see what it is, you force it into either the zero-fifth state or the one-earth state. You lose the quantum information encoded in that vector. That's a massive difference from classical bits, where you can always just read the value 0 or 1 without fundamentally changing it.
Wow, okay. That's already mind-bending. If it's not definitely 0 or 1, and you can't just look at it, what is it doing? This sounds like it leads straight into superposition.
You got it. Superposition. This is probably one of the most famously counterintuitive, but also most powerful ideas in quantum mechanics.
The quantum weirdness starts here.
It really does. Think about flipping a regular coin. While it's spinning in the air, you might not know the outcome, but you know it will land as either heads or tails.
Right? It's one or the other eventually.
But a qubit is different. Before you measure it, it can exist in a superposition, a mathematical combination of both the 0 state and the 1 state at the same time. It's not just uncertain, it's literally in a blend of both possibilities.
Okay, wait, not like it's rapidly flipping between 0 and 1.
No, not flipping. Think of it more like, imagine mixing two colors, say red and blue. You don't get flipping red, blue, you get purple. A new state that has characteristics of both.
Okay. A combination state. But how do we even picture that? Our brains aren't really wired for both at once.
They really aren't. That's why visualization tools are helpful, even if they're just analogies. Physicists often use something called the Bloch sphere.
The Bloch sphere?
Right. Imagine a perfect globe. We can say the 0 state is at the North Pole and the 1 state is at the South Pole.
Okay. Classical bit. Only North Pole or South Pole.
Exactly. But a qubit. Its state can be represented by a point anywhere on the surface of that sphere.
Anywhere. On the equator. Somewhere in the northern hemisphere.
Anywhere. And its exact location on the sphere, its latitude and longitude, if you will, tells you the precise mathematical relationship between the 0 component and the 1-airship component in its superposition. The closer the point is to the North Pole, the higher the probability you'll measure it as 0U. Closer to the South Pole, higher probability of measuring 1 here.
So the position is that vector you mentioned earlier, basically defining the probabilities.
It represents the vector, yes. It encodes those probability amplitudes.
And you mentioned complex numbers before. This is where they come in, isn't it? My brain starts to ache a bit thinking about imaginary numbers controlling reality. Why are they needed here?
Yeah, complex numbers are essential. The state is often written as uso plus su or yo. Alpha and beta are these complex numbers.
Okay.
Now, don't get too hung up on the imaginary part. For quantum mechanics, think of complex numbers as having two parts, a magnitude and a phase. The magnitude squared gives you the probability, AC is the probability of measuring 0, is the probability of measuring 1, and these probabilities have to add up to 1, naturally.
Right, something has to happen.
But the phase part, that's crucial. It's like a direction associated with that amplitude. And these phases are what allow for quantum interference.
Interference, like waves canceling each other out or adding up.
Exactly like waves. Just like water waves can combine to make bigger waves, constructive interference, or cancel each other out, destructive interference, these quantum probability amplitudes can interfere. This interference is the secret sauce. It allows quantum algorithms to amplify the probability of getting the right answer while simultaneously canceling out the probabilities of getting the wrong answers. That's key to quantum speedup.
So the complex numbers aren't just bookkeeping. They enable this wave-like interference effect for probabilities. That's wild.
It is pretty wild. It's fundamental to how quantum computers gain their advantage.
Okay, so the qubit is in this blended, probabilistic wave-like state. Nasse plus Edier, hovering somewhere on the Bloch sphere. But eventually we need an answer, right? A classical 0 or 1. What happens when we actually measure the qubit?
Measurement is the moment of truth, you could say. When you perform a measurement on a qubit, that's in superposition, its state instantaneously collapses.
Collapses?
Yes, it collapses from that probabilistic blend, that point on the sphere, down to one of the definite classical states, either 0 yay, North Pole, or 1 cis South Pole.
And which one it chooses is random.
It's fundamentally probabilistic. The outcome isn't predetermined before the measurement. The probabilities are given by those squared magnitudes we talked about, Elton Taft. This rule for calculating probabilities from the state vector is called Born's rule.
So if a qubit is in a state where Einstein tach have equal magnitude, like right on the equator of the Bloch sphere,
then you have an exactly 50-50 chance of measuring 0 euro, or 1 EO. This is precisely what happens, for example, if you start with a qubit in the 0 state and apply a special operation called a Hadamard gate. It puts it into that perfect 50-50 superposition. Measure it, and you get a truly random outcome.
That's the basis for quantum random number generation we hear about.
That's exactly it, the inherent randomness of quantum measurement.
So the quantum coin flip analogy is pretty good that it's spinning in superposition, but once it lands, once you measure it, it's definitively heads or tails, 0 or 1.
Precisely. But the act of landing, the measurement itself, is crucial. It fundamentally changes the state.
Changes it. How so?
Unlike classical information, think of a file on your computer which you can copy millions of times without altering the original.
Right.
You absolutely cannot perfectly copy an unknown quantum state. This is a fundamental principle called the no-cloning theorem.
No cloning, so you can't just make a backup of your qubit's state.
Nope. Because to find out the state in order to copy it, you'd have to measure it. And measuring it, as we just said, collapses the superposition and forces it into a definite 0 or 1. You've destroyed the very quantum information, the specific cavity you were trying to copy.
Wow. Okay, that has huge implications. Like, how do you even debug a quantum program if you can't check the state of your qubits halfway through?
Exactly. It makes designing, testing, and debugging quantum algorithms and hardware incredibly challenging compared to classical computing. You can't just insert print statements everywhere to see the values of your quantum variables. Interacting with them changes them. It's a whole different paradigm.
A fundamental difference, no cloning. Measurement changes the state. Got it. But we can manipulate qubits before we measure them, right? While they're still in superposition. That's how algorithms work.
Yes, absolutely. And that's where quantum operations, or more commonly, quantum gates, come in.
Quantum gates. Analogous to classical logic gates like A and D or not T.
Similar in purpose, manipulating the information, but fundamentally different in operation. Think of quantum gates, not as simple switches, but as precise controlled transformations of the qubit state vector.
Transformations, like moving that point around on the Bloch sphere.
Exactly. Applying a quantum gate is like performing a specific smooth rotation of the state vector on the surface of the Bloch sphere. Mathematically, these rotations are represented by special types of matrices called unitary matrices.
Unitary matrices. Okay, sounds technical. What's important about them being unitary?
The key thing is that unitary operations are reversible. Quantum computations, before measurement, need to be reversible to preserve the quantum information. They also ensure that the total probability stays 1, that the length of the state vector remains constant as it's rotated. It keeps the quantum state valid and coherent until we're ready to measure.
So, not like classical gates, some of which are irreversible, like A and D. Quantum gates are more like these elegant reversible dances on the Bloch sphere. What are some of the essential ones we should know about? Building blocks.
Great question. Let's start with maybe the most intuitive one, the Pauli X gate.
X gate, okay.
This is the quantum version of the classical Nati gate. It flips the 0 state to the 1U state, and it flips 1 euro back to 0.
Simple flip, like the light switch.
Pretty much. On the Bloch sphere, it corresponds to a 180-degree rotation around the x-axis. It takes the North Pole to the South Pole and vice versa. Fundamental.
Makes sense. What else is in the basic toolkit?
Next up, and absolutely crucial, is the Hadamard gate, usually just called the H gate.
Hadamard, I've heard that one mentioned a lot.
You probably have, because this gate is the workhorse for creating superposition. It's central to almost everything in quantum computing. If you start with a qubit in the 0 state, North Pole, and apply a Hadamard gate,
What happens?
it transforms it into that perfect equal superposition of 0 RO and 1 UR. The state becomes 0A plus 1 URO. That point moves from the North Pole to a specific spot right on the equator of the Bloch sphere.
The 50-50 state. The quantum coin flip state.
Exactly. Measure it now, and you get 0, 1 with equal probability. The Hadamard gate is the key ingredient for unlocking quantum parallelism and, as we discussed, for quantum random number generation.
So the X gate flips, the H gate creates superposition. It feels like the H gate is the magic wand here.
It's definitely one of the most important tools. We also have the poly Y gate and poly Z gate.
More rotations.
Yep. They perform 180-degree rotations around the y-axis and z-axis of the Bloch sphere, respectively. The Z-gate, for instance, leaves 0 I's unchanged, but multiplies the 1R state by -1, so it changes the phase of the 1R component.
Phase again, that interference thing?
Precisely. Flipping the sign might seem subtle, but changing the phase is critical for controlling how different quantum states interfere with each other in more complex algorithms. Constructive or destructive interference depends crucially on these relative phases.
Okay. X, Y, Z for basic rotations flips, H for superposition. Is that enough? Can you build any quantum computation with just these?
Almost. You need these single qubit gates, which allow you to rotate any single qubit to any point on its Bloch sphere. But to get the real power, especially entanglement, you need at least one type of 2-qubit gate as well.
Involving interactions between qubits.
Exactly. The amazing thing is, it's been proven that a finite set of gates, typically all possible single qubit rotations, plus just one specific type of 2-qubit gate, like the CNOT gate we'll discuss, is sufficient to approximate any possible quantum computation to any desired accuracy. This is called a universal gate set.
Wow. So like classical computing has NAND gates as universal, quantum has its own small set. That's quite elegant.
It is. It means that building a universal quantum computer boils down to being able to reliably implement these fundamental single and 2-qubit operations.
Okay, this is painting a clear picture. We have qubits that can be 0, 1, or both superposition. We can manipulate them with gates, rotations. But you mentioned the real power comes from interactions, which brings us to entanglement.
Yes, entanglement. If superposition stretches our intuition, entanglement often breaks it completely.
Einstein's spooky action at a distance. That phrase alone tells you it's weird.
It's incredibly weird, but incredibly powerful. Entanglement is a purely quantum phenomenon where 2 or more qubits become linked in such a profound way that they essentially behave as a single system, no matter how far apart they are physically.
Linked. How? More than just, say, 2 coins that are correlated because they came from the same mint.
Oh, much, much deeper than any classical correlation. With entangled qubits, their individual fates are intertwined. Measuring the state of one qubit instantaneously influences the state of the other it's entangled with, regardless of the distance separating them.
Instantaneously. Faster than light. That sounds like it breaks physics.
It sounds like it, but it doesn't actually allow for faster than light communication. You can't use it to send a message instantly. But the correlation is instantaneous. It's one of the deepest mysteries and most powerful resources in quantum mechanics.
Okay, I need an example. How does this work?
A classic example is a specific entangled state of 2 qubits called a Bell state. One common Bell state can be written as 00 plus 11 0.
Okay, what does that mean? 00 means both qubits are 0. 11ers means both are 1.
Exactly. So this state is a superposition of the first qubit being 0 AD, the second being 0, combined with the first qubit being 1 AD, the second being 1. Before you measure, neither qubit has a definite value. Qubit 1 isn't 0 or 1. Qubit 2 isn't 0 or 1.
Right, they're in superposition.
But they are perfectly correlated. If you measure the first qubit and find it to be 0, instantly, with 100% certainty, that the second qubit, no matter where it is, will also be measured as 0.
Wow.
And if you measure the first qubit as 1, you know the second one is instantly 1. Their individual outcomes are random, 50-50 chance of 0 or 1 for the first qubit, but the results are perfectly locked together.
That is spooky. They somehow know about each other instantly.
That's the non-classical correlation. And mathematically, how do we represent states of multiple qubits? We use something called the tensor product. When you combine the state spaces of multiple qubits, you get states that sometimes cannot be broken down or factored into descriptions of individual independent qubits. Those inseparable states are the entangled states.
Okay, tensor products. Entanglement. It's getting complex, but I see the core idea. This deep non-local connection.
Yeah.
How do you actually create this entanglement? You mentioned 2-qubit gate.
Precisely. Entanglement doesn't just happen. You need gates that allow qubits to interact. The most fundamental 2-qubit gate is the controlled NOT gate, or CNOT.
CNOT, controlled NOT. What does it do?
It involves 2 qubits,
Yeah.
a control qubit and a target qubit. The gate does the following. If the control qubit is in the 0A state, it does absolutely nothing to the target qubit.
Okay.
But if the control qubit is in the 1O state, then it applies a NOT gate, an X gate, to the target qubit, flipping it.
So the state of one qubit controls whether an operation happens on another qubit. Conditional logic, but quantum style.
Exactly. And if you apply a CNOT gate, when the control qubit is in a superposition of 0 and 1C, say after Idemard gate, that's how you create entanglement, like the Bell state we just discussed.
Yeah.
The CNOT gate is the fundamental building block for creating these crucial correlations and for enabling complex quantum algorithms.
So CNOT is the key to linking qubits together in these spooky ways.
It's a cornerstone. And many other quantum operations can also be applied conditionally based on the state of other qubits. This conditional execution is vital for building sophisticated quantum circuits.
This really starts to feel like where the computational power emerges: superposition to explore possibilities, entanglement to correlate them, and gates to manipulate them.
You've got it. Those are the key ingredients.
Okay, let's connect this back to something concrete. We mentioned quantum random number generation, QRNG. You said it uses superposition and measurement. Why is this so much better than what we currently use? Talk about classical randomness again.
Right. So most random numbers used in classical computers today are actually pseudorandom. They're generated by deterministic algorithms.
Algorithms, so predictable recipes.
Exactly. They start with an initial value called a seed, and then use a mathematical formula to produce a sequence of numbers that looks random and passes statistical tests for randomness. But if you know the algorithm and you know the seed,
you can predict the entire sequence. It's not truly random at all.
Right, so it's predictable if you have enough information or computational power. Remember that story about the Press Your Luck game show in the 80s?
Vaguely. Someone cracked the code.
Yeah, a guy named Michael Larson figured out the supposedly random pattern of the light moving around the game board wasn't random at all. It used only a few repeating patterns. He memorized them, hit the button at the right times, and won a fortune because he could predict the random outcomes.
Wow, that's a perfect, if slightly alarming, example of pseudo-randomness failing.
It really is. It highlights the potential vulnerability. If the randomness isn't physically guaranteed, it can potentially be broken.
So how does quantum mechanics provide that physical guarantee? You mentioned the Hadamard gate and measurement.
It leverages the inherent, irreducible randomness of quantum measurement. The process is beautifully simple. 1. Prepare a qubit in a definite starting state, typically 0J. 2. Apply a Hadamard H gate. This puts the qubit into the perfect 0-2 superposition, that 50-50 state. 3. Measure the qubit.
And because measurement collapses the superposition probabilistically.
The outcome, whether you get a 0 or a 1, is fundamentally random according to the laws of quantum mechanics. It's not just hard to predict, it's impossible to predict with certainty beforehand, even in principle.
Impossible without breaking physics itself. That's a much stronger guarantee than it's hard to compute.
Exactly. This provides what's called information theoretic security for the randomness source. An adversary can't predict the numbers unless they can violate quantum mechanics. This is a world away from classical computational security, like RSA encryption, which relies on assumptions about problems like factoring being computationally hard for classical computers.
Assumptions that Shor's algorithm might break.
Precisely. QRNG offers randomness guaranteed by physics, making it a foundational element for future secure systems.
A huge deal for security. Okay, moving beyond randomness, let's talk about the algorithms that promise these massive speedups for complex problems. This is the quantum advantage everyone's chasing.
Indeed. This is where we see the potential for quantum computers to tackle problems currently intractable for even the world's fastest supercomputers. It's not about speeding up email. It's about solving specific hard problems much, much faster.
Let's start with a famous one, Grover's algorithm. What problem does it solve, and what kind of speedup are we talking about?
Grover's algorithm tackles the problem of unstructured search. Imagine you have a huge database, like that phone book example. 1 million entries, but it's completely unsorted. You're looking for one specific entry, the marked item.
Okay, like finding a needle in a haystack. Classically, you just have to look one by one, right?
Pretty much. On average, you'd expect to check about half the entries, 500,000 in our example. In the worst case, you might have to check every single one, 1 million. We say this takes time proportional to the number of items, n. So classically, it's O(n) complexity.
Linear scaling. More items, proportionally more time. How does Grover do better?
Grover's algorithm provides a quadratic speedup. It can find the marked item in roughly O(n) steps, or queries to the database.
Square root of n. So for a million items, instead of to a million steps, it's closer to the square root of a million, which is only 1,000.
Exactly. From a million down to 1,000, that's a massive improvement, especially as n gets very large.
That's incredible. How does it achieve that? It doesn't check them one by one, obviously.
No, it uses superposition and interference in a very clever way. First, it puts all the possible items or indices into a uniform superposition. Think of it as considering all possibilities at once.
Okay, leveraging superposition.
Then, it performs a sequence of operations that act like reflections. It repeatedly applies two main steps. One that flips the sign, changes the phase, of the marked item's amplitude, and another that reflects all amplitudes around the average amplitude.
Reflections, like in a mirror.
Kind of. The effect of these reflections is to systematically increase the amplitude, and thus the measurement probability, of the correct marked item, while decreasing the amplitudes of all the incorrect items. Each repetition nudges the quantum state closer to the solution.
So it's like amplifying the signal of the right answer while canceling out the noise of the wrong ones.
That's a great way to put it. It uses interference to amplify the desired state. After about cent repetitions, the probability of measuring the correct item becomes very high.
Quadratic speedup for search. Very cool. What about Deutschklasse? That one sounds more theoretical, like a proof of concept.
The Deutschklasse algorithm was one of the very first algorithms to show a potential exponential speedup over classical methods back in 1992. It addresses a specific, somewhat contrived problem, but it beautifully illustrates quantum power.
Okay, what's the problem?
You're given a function, a black box or oracle, that takes a binary string as input and produces either 0 or 1 as output. You're promised that the function is either constant, it always outputs the same value, either 0 for all inputs or 1 for all inputs, or balanced, that outputs 0 for exactly half the possible inputs and 1 for the other half. Your job is to figure out which type it is, constant or balanced, using the minimum number of calls to the oracle.
Okay. Classically, how would you do that? You'd have to test inputs, right?
Right. If you test one input and get, say, 0, you don't know much yet. If you test another and get 1, you immediately know it's balanced. But if you keep getting zeros, you need to check more than half the input to be absolutely sure it's constant and not just balanced in a way you haven't seen yet. In the worst case, classically, you might need two n1 plus 1 queries, where n is the number of input bits, exponential in the input size.
Okay, potentially many queries. How does Deutschklasse do it?
Deutschklasse can determine whether the function is constant or balanced with just one single query to the quantum oracle.
One query. Exponential speedup. How?
It uses superposition to evaluate the function for all possible inputs simultaneously. It prepares the input qubits in a superposition of all possible input strings, queries the quantum oracle, which acts on the superposition, and then uses quantum interference, specifically the quantum Fourier transform, or a simpler version using Hadamard gates, to cleverly arrange things so that the final measurement outcome directly reveals whether the function was constant or balanced.
So it learns a global property of the function, constant versus balanced, in one shot by leveraging superposition and interference.
Precisely. While the problem itself isn't directly practical, it was a landmark result showing that quantum computers could, in principle, solve certain problems exponentially faster than classical ones.
Mind-blowing potential. Okay, now for the big one. The algorithm causing sleepless nights in the cryptography world. Shor's algorithm.
Ah, Shor's. Developed by Peter Shor in 1994. This is arguably the most impactful quantum algorithm discovered so far because it tackles a problem at the heart of modern digital security.
Which is?
Factoring large integers into their prime numbers.
Factoring numbers. Like finding that 15 is 3 times 5, that seems easy.
Is for small numbers. But try factoring a number with, say, 600 digits. For a classical computer, this is an extremely hard problem. Finding the two large prime numbers that were multiplied together to get that 600-digit number could take the most powerful supercomputers billions of years.
Billions of years. Wow. And this hardness is what keeps our data safe online.
Exactly. The security of widely used public key encryption systems like RSA, used for secure websites, HTTPS, encrypted emails, digital signatures, relies directly on the assumption that factoring large numbers is practically impossible for classical computers.
Okay, so what does Shor's algorithm do to that assumption?
Shor's algorithm provides a way for a sufficiently powerful quantum computer to factor large numbers efficiently in polynomial time, meaning the time it takes scales gently, like a polynomial function, with a number of digits, not exponentially like classical algorithms.
Polynomial time. So instead of billions of years, it might take hours, minutes.
Potentially, yes. For numbers large enough to be secure classically, A fault-tolerant quantum computer running Shor's could factor them relatively quickly, rendering RSA and similar schemes completely insecure.
That is a game changer, an existential threat to current cryptography. How does it work? Without getting too deep in the math.
The core insight is brilliant. Shor's figured out how to transform the factoring problem into a different problem, finding the period of a specific mathematical function related to the number you want to factor.
Period finding, like finding the length of a repeating pattern.
Exactly, like finding the wavelength of a wave. It turns out that if you can find the period of this particular function efficiently, you can use that information to calculate the factors of the original large number relatively easily.
And quantum computers are good at period finding.
Exceptionally good. This is where the quantum Fourier transform, QFT, comes in again. The QFT is a quantum version of the classical Fourier transform, and it's incredibly efficient at identifying periodicities hidden within quantum states. Shor's algorithm uses the QFT to find the period of that special function, and from there derives the factors. It beautifully leverages quantum parallelism and interference to solve a classically hard number theory problem.
Amazing. So it finds a hidden pattern using quantum tricks, and that pattern unlocks the factors.
That's the essence of it. It's why there's such a huge effort underway to develop post-quantum cryptography, new encryption methods resistant to Shor's algorithm.
We'll definitely come back to that. But first, let's broaden out from these foundational algorithms. Where else might quantum computing make a real-world impact? You mentioned simulating molecules earlier.
Yes, quantum simulation is one of the most promising near-term applications. Quantum computers are inherently quantum mechanical systems themselves.
Right, using quantum to understand quantum.
Exactly. It makes them naturally suited to simulate other quantum systems like atoms, molecules, and the behavior of materials at the quantum level. Classical computers really struggle with this.
Why is it so hard classically?
Because accurately simulating quantum effects, especially things like electron correlation, how electrons interact and influence each other's positions and energies within a molecule, requires computational resources that grow exponentially with the size of the system. Even for relatively small molecules, the complexity becomes overwhelming for classical machines.
So calculating, say, the precise energy state of a complex drug molecule is just impossible classically.
Calculating it with perfect quantum accuracy, yes. We use approximations, but they have limitations. The fundamental equation governing these systems is the Schrödinger equation. Solving it accurately is the key. Quantum computers could potentially simulate these systems directly, mapping the molecule's electrons and interactions onto qubits and quantum gates.
And the payoff could be huge.
Immense. Imagine designing new catalysts for industrial processes, discovering novel drugs by accurately predicting how they'll interact with target proteins, or engineering materials with desired properties like high-temperature superconductivity or better energy storage for batteries. Quantum simulation could revolutionize chemistry, materials science, and medicine.
Simulating nature's building blocks. Powerful stuff. Now, what about finance? Our source material really dug into this. You mentioned stochastic modeling and Monte Carlo methods.
Right. Finance relies heavily on Monte Carlo integration, MCI. Think about pricing complex financial derivatives, like options, or assessing the risk of a large investment portfolio. These tasks involve simulating thousands, even millions, of possible future market scenarios to estimate an average outcome or risk level.
Running simulations over and over to get a statistical picture.
Exactly. And classically, achieving high precision with Monte Carlo requires a huge number of simulation runs, which translates to significant computational time and cost. There's often a trade-off. Faster results might mean lower accuracy.
So banks and hedge funds spend a fortune on computing power for this. How can quantum help?
There's a known quantum algorithm for quantum Monte Carlo integration, QMCI, that offers a provable quadratic speedup in achieving a certain level of precision compared to classical Monte Carlo.
Quadratic speedup again, like Grover's.
Yes. It means you can reach the desired accuracy with quadratically fewer samples or simulation steps. Our sources show this clearly in graph figure 2. The quantum algorithm's error drops much faster than the classical one as you increase the number of samples. The blue line, quantum, is consistently below the orange line, classical, and the gap widens.
So potentially much faster and more accurate financial modeling.
That's the promise. Faster pricing of derivatives, better risk analysis, quicker reaction to market changes. It could provide a significant competitive edge.
Beyond Monte Carlo, what about other financial problems? Optimization came up.
Yes, optimization problems are everywhere in finance. A classic example is portfolio optimization. trying to select the best mix of assets, stocks, bonds, etc., to maximize expected return for a given level of risk tolerance, often subject to many complex constraints.
Finding the perfect balance in a huge sea of possibilities sounds hard.
It's typically an NP-hard problem, meaning the complexity explodes as you add more assets or constraints. Quantum approaches like quantum annealing, QA, pioneered by companies like D-Wave, and variational algorithms like the variational quantum eigensolver, VQE, run on gate-based machines, are being explored to tackle these optimization problems more effectively than classical solvers, especially when the constraints get really complicated.
So potentially better investment strategies.
Potentially, yes. Or even more ambitious things, like analyzing the complex network of interdependencies in the financial system to try and predict systemic risks or potential crashes. Modeling these intricate networks can also be viewed as NP-hard optimization or simulation problems, where quantum might offer an advantage.
Predicting crashes, that would be something. And then there's the intersection with another huge field, machine learning, QML and finance.
Quantum machine learning, QML, is a very active, though still quite speculative, area. The general idea is to leverage quantum phenomena like superposition and entanglement to potentially analyze vast financial data sets in new ways, find subtle patterns, or optimize machine learning models faster or more powerfully than classical ML.
What are some potential applications people are looking at?
Anomaly detection is a big one, particularly for fraud detection. Could QML algorithms spot fraudulent credit card transactions or identify suspicious patterns in financial documents more effectively than current systems?
Yeah.
That's a key research
I
question.
think that alone would be hugely valuable.
Absolutely. Other areas include potentially more accurate asset pricing by processing complex market data faster or calculating things like implied volatility more efficiently. Researchers are developing concepts like quantum neural networks, QNNs, hoping to build quantum analogs of classical deep learning models that might offer advantages for certain types of financial prediction or analysis tasks.
So huge potential across simulation, optimization, and machine learning in finance. But let's ground ourselves again. We're talking about the potential. What's the reality of the hardware right now? You mentioned NISQ devices earlier.
Yes, NISQ. It stands for Noisy Intermediate Scale Quantum. And that acronym perfectly captures the state of current quantum hardware.
Okay, break that down. Noisy.
Noisy means these quantum computers are highly susceptible to errors. Qubits are incredibly delicate. Tiny fluctuations in temperature, stray electromagnetic fields, even vibrations can disrupt their quantum states, superposition, entanglement, causing errors in the computation. This loss of quantum coherence is called decoherence, and it's the arch nemesis of quantum computing.
So the calculations aren't perfect. They have static.
Lots of static. Noise limits the depth of calculations you can perform before the errors overwhelm the result.
Okay, that's noisy. What about intermediate scale?
Intermediate scale refers to the number of qubits. Current devices typically have anywhere from a few dozen to maybe a few hundred qubits. While that's impressive progress, it's generally not enough to run the really large, powerful, error-corrected algorithms like Shor's for breaking realistic encryption or performing truly massive simulations.
So noisy and not quite big enough yet for the killer apps. That's the NISQ era reality.
That's the current reality, yes.
Yeah.
It means researchers are focused on finding useful algorithms that can run on these imperfect machines or demonstrating quantum advantage on specific tasks despite the noise.
And who is actually building these NISQ machines? What kind of physical systems are they using for qubits? It's not just one approach, right?
Not at all. It's a fascinatingly diverse landscape, a real horse race of different technologies, each with pros and cons. One of the most mature and widely used approaches is superconducting qubits.
That's the tech used by IBM and Google.
Yes, and Rigetti, among others. These typically use tiny electrical circuits made from superconducting materials, cooled down to incredibly low temperatures near absolute zero.
In those big, fancy refrigerators?
The chandeliers, exactly, those dilution refrigerators. The qubits are based on quantum states within these circuits, like the energy levels of Cooper pairs of electrons. They offer relatively fast gate operations and good scalability potential, but require that extreme, complex cooling infrastructure.
Okay, superconducting circuits in the ultra-cold. What's another major approach?
Another leading contender is trapped ion qubits. Companies like IonQ, Quantinuum, formerly Honeywell Quantum Solutions, and AQT are big players here.
Trapped ions, so individual atoms.
Precisely. They take individual atoms, strip an electron arc to give them a positive charge, ionize them, and then trap these ions using electromagnetic fields in an ultra-high vacuum. They hover in space.
Oh.
Then they use precisely tuned lasers to cool the ions down, initialize their quantum states using internal energy levels as the qubit state's 0 array, perform gate operations by shining lasers on specific ions, and read out the results.
What are the advantages there? Sounds delicate.
Trapped ions are known for having very high fidelity, meaning the gate operations are extremely accurate, with low error rates and very long coherence times, meaning the qubits can maintain their quantum states for much longer before decoherence sets in, compared to some other technologies. The main challenge has historically been scaling up to large numbers of ions while maintaining individual control and fast interactions.
High quality, maybe harder to scale. Superconducting, faster, maybe noisier, needs extreme cold. Interesting trade-offs. Are there other promising technologies in the race?
Oh, absolutely. It's a very active field. Photonic systems are being pursued by companies like Sequantum and Xanadu. They use individual particles of light photons as qubits.
That's made of light?
Yep. The potential advantages include operating at room temperature, or near it, and leveraging existing fiber optic technology. The big challenge is getting photons, which don't naturally interact much, to perform strong 2-qubit gates efficiently.
Okay, photons. What else?
There's also neutral atoms. Companies like Cold Quanta, now Inflection, and atom computing are trapping large arrays of neutral, uncharged atoms using laser fields, called optical tweezers or lattices. They use internal states as qubits and can potentially scale to thousands of qubits relatively easily. Controlling interactions and maintaining coherence are key areas of research.
Neutral atoms sounds similar to trapped ions, but without the charge.
Similar principles, different techniques and trade-offs. And then there are approaches like spins in silicon or quantum dots, trying to leverage the existing, incredibly advanced semiconductor manufacturing industry to create qubits based on the quantum spin of electrons trapped in silicon structures. Each path has passionate proponents and faces unique scientific and engineering hurdles.
It really is a technological race on multiple fronts. So much ingenuity. But if all these current NISQ devices are inherently noisy, how do we ever get to the point of running something like Shor's algorithm reliably? You need accuracy for that, right?
Absolutely. That's the billion-dollar question, maybe $1 trillion. The noise, the errors, the decoherence, this is the fundamental obstacle between the NISQ era and the era of truly powerful, fault-tolerant quantum computing.
Fault-tolerant, meaning it can handle the errors.
Exactly. We need to build machines that can perform computations correctly, despite the fact that their underlying physical components are imperfect and constantly experiencing noise.
But how? If the qubits themselves are faulty?
The solution lies in quantum error correction, QEC. This is a whole field dedicated to protecting fragile quantum information from noise.
Error correction, like in classical computers. Checksums and stuff.
Similar in spirit, but much more complex due to quantum mechanics, especially the no-cloning theorem. You can't just copy a qubit to check it. Instead, QEC involves encoding the information of a single logical qubit, the perfect, idealized qubit you want to compute with, across many physical qubits.
Using redundancy, like storing the same data in multiple places.
As a very clever form of redundancy. The information is encoded in the correlations and entanglement patterns across a group of physical qubits. This encoding is done in such a way that common types of errors like a bit flip, a 0-0 accidentally flipping to 1R, or a phase flip, that subtle sign change we talked about, affecting one physical qubit can be detected and corrected without actually measuring and destroying the logical qubit's state.
So you can find and fix errors without looking at the sensitive quantum data directly.
That's the magic of QEC codes. The famous Shor code, yes, same Peter Shor, was an early example showing this was possible, using 9 physical qubits to protect one logical qubit against both bit flips and phase flips. Modern codes like surface codes are considered more practical for building large-scale machines. They have nice properties, like only requiring interactions between nearby physical qubits, which is easier to engineer.
Surface codes. Okay, so QEC protects the logical qubits. Is that the same as fault tolerance?
QEC is a crucial part of fault tolerance, but fault tolerance is a property of the entire system. It means not only can you correct errors in the qubits at rest, but you can also perform logical gate operations on these encoded qubits in a way that prevents errors from propagating or multiplying uncontrollably. Even the error correction process itself must be fault tolerant, meaning it needs to correct errors faster than new errors are introduced by the process itself.
Wow. That sounds incredibly complex, building layers of protection on top of already complex hardware.
It is arguably the single biggest scientific and engineering challenge facing the field. Achieving fault tolerance requires extremely low error rates in the physical qubits and gates to begin with, plus sophisticated control systems and architectures.
So the road to robust, fault-tolerant hardware, what's the timeline? Are we talking years, decades? When might we see a quantum computer that can actually break RSA?
That is the multi-million, maybe billion-dollar question everyone wants the answer to. The honest answer is nobody knows for sure. Estimates vary wildly. Some optimists talk about significant progress within 5–10 years, while others think true, large-scale, fault-tolerant machines capable of threatening current encryption standards are likely 15–20 years away, or even more. It depends heavily on continued scientific breakthroughs and massive engineering efforts. We're making progress, but the hurdles are substantial.
A marathon, not a sprint, sounds like. Okay, so immense technical challenges remain, but assuming we eventually get there, or even as we progress, what are the broader impacts? Let's circle back to security post-quantum cryptography, PQC.
Right. Given the threat Shor's algorithm poses, we can't wait for fault-tolerant quantum computers to arrive before we act. The global cybersecurity community is actively working on migrating to PQC.
New encryption methods that are safe from quantum attacks.
Exactly. PQC involves developing and standardizing new cryptographic algorithms based on mathematical problems believed to be hard for both classical and quantum computers. These problems often come from areas like lattice-based cryptography, hash-based signatures, or multivariate cryptography. The idea is to find problems where quantum algorithms like Shor's don't offer a significant advantage.
And who's leading this effort?
The U.S. National Institute of Standards and Technology, NIST, is running a major international competition to select and standardize the best PQC algorithms. They've already announced several winners and finalists after years of rigorous analysis by cryptographers worldwide. Governments and industries are now starting the long process of upgrading systems to use these new PQC standards.
So we're actively building defenses before the threat fully materializes. Smart.
It's essential. And we'll likely see hybrid approaches, too, maybe combining classical PQC with emerging quantum technologies like quantum key distribution, QKD, which uses quantum physics principles for a secure key exchange, and the QRNGs we discussed, to create multiple layers of security.
A belt-and-suspenders approach for the quantum era. Makes sense. Now, beyond security, what about other societal or ethical considerations? We touched on AI bias. Is bias in quantum algorithms a concern, too?
It absolutely is, and it's crucial we think about it now, early in the development cycle. Just like classical AI systems, quantum algorithms, especially QML, can inherit and even amplify biases.
Where does the bias come from?
Several places. If you train a QML model on biased data that reflects historical inequalities or underrepresents certain groups, the quantum algorithm will likely learn and perpetuate those biases. Bias can also be baked into the algorithmic design itself, perhaps in how the problem is framed or which features are prioritized, and potentially even hardware imperfections if certain qubits or gate operations are consistently less reliable for specific types of inputs could introduce subtle systemic biases into the results.
And the consequences could be really serious, right? If these are used for loan applications, medical diagnoses, hiring.
Exactly. The risk is creating or reinforcing unfair discriminatory outcomes in high-stakes decisions. Imagine a quantum-powered financial tool that disadvantages certain communities, or a healthcare application that's less accurate for specific demographics. It's vital that fairness, accountability, and transparency are core principles in QML development. We need proactive strategies, careful data auditing, bias mitigation techniques built into the algorithms, rigorous testing across diverse groups. Ethics can't be an afterthought here.
A critical warning, which connects to another potential issue, the quantum divide. What's the worry there?
The quantum divide refers to the concern that the benefits and access to powerful quantum computing technologies might be unevenly distributed, exacerbating existing inequalities.
Like a gap between the quantum haves and have-nots.
Precisely. If only wealthy nations, large corporations, or elite research institutions can afford to build or access advanced quantum computers, they could gain significant advantages in science, medicine, finance, and defense, potentially leaving others further behind. This could widen the gap between developed and developing countries, or even within societies.
So how do we prevent that?
It highlights the importance of promoting broader quantum literacy and education globally. We also need to encourage open access initiatives, like the cloud platforms we discussed, which allow researchers and developers worldwide to experiment with quantum resources without needing to own the hardware. Fostering international collaboration and ensuring that the benefits are shared widely are key challenges as the field matures.
Building the tech responsibly and accessibly. Okay, let's zoom out a bit and look at the overall ecosystem. Who are the main players pushing this forward? You've mentioned several companies.
It's a really vibrant mix of big tech, specialized startups, government labs, and universities. On the company side, you have major players like IBM, Google, Microsoft, who are exploring topological qubits, investing heavily, primarily in superconducting qubits. Then specialized companies like IonQ and Quantinuum leading in trapped ions. D-Wave focuses on quantum annealers, so Quantum and Xandu are betting on photonics. Inflection, cold quanta, and atom computing are pushing neutral atoms, and many, many others developing hardware, software, and applications.
A diverse field. And you mentioned cloud platforms as key for access.
Yes, cloud access is crucial. Platforms from IBM, Google Cloud, AWS, Amazon Bracket, Microsoft Azure, Quantum, Rigetti, IonQ, Quantinuum, and others allow users to submit quantum jobs to various types of real quantum hardware over the internet. This democratizes access significantly.
And who are the end users exploring these platforms and potential applications?
It's expanding. Initially, mostly academic researchers and national labs. But now, increasingly, companies in pharmaceuticals like Roche, Boehringer Ingelheim, material science like BASF, Dow, finance, JP Morgan Chase, Goldman Sachs, automotive BMW, Volkswagen, aerospace, Airbus, Lockheed Martin, and logistics are setting up quantum teams or partnerships to explore how this technology could impact their industries.
So real industries are kicking the tires now.
They are, and collaboration is key. We see lots of partnerships between hardware providers, software companies, academic groups, and these potential end-user industries to try and find near-term applications and build the quantum workforce.
And one last term we sometimes hear, especially when companies announce breakthroughs, quantum supremacy. What exactly is that, and how does it fit in?
Quantum supremacy, or maybe a better term, is quantum computational advantage, refers to a specific experimental milestone. It's the point at which a quantum computer demonstrably performs a specific computational task that is practically impossible for even the most powerful classical supercomputer to perform in a reasonable amount of time.
So it's about proving the quantum computer can do something classically impossible, even if that something isn't immediately useful.
Exactly. The tasks used for these demonstrations, like Google's Sycamore experiment in 2019 or experiments from researchers in China, are often highly specialized, even contrived, like sampling random output distributions from complex quantum circuits. They don't necessarily solve a pressing real-world problem.
So why is it important then? Bragging rights.
It's more than bragging rights. It's a crucial scientific validation. It provides empirical evidence that quantum computers can, in principle, operate in a computational regime beyond classical capabilities, confirming the underlying theory. It's a proof of concept that the whole endeavor isn't just theoretical, that these machines can actually tap into quantum power, even if harnessing it for useful applications on noisy devices is still a major challenge. It shows the potential is real.
Got it. A scientific benchmark proving the principle works.
Precisely. A stepping stone on the long road towards fault-tolerant, useful quantum computation.
Wow. What an incredible journey we've taken in this deep dive. We started right at the beginning, making that leap from the familiar world of classical bits, the definite zeros and ones, to the truly strange nature of qubits, existing in that fuzzy state of superposition, being both 0 and 1 until you look.
And we saw how measuring them forces a collapse into a definite but probabilistic outcome. No peeking allowed without changing things.
Then we dove into the real power multipliers, that spooky entanglement linking qubits across space, and the promise of algorithms like Grover speeding up search quadratically.
And Shor's algorithm, the cryptographic game changer, offering an exponential speedup for factoring, threatening our current digital security foundations.
We then explored how these mind-bending concepts might translate into real-world value, simulating molecules for drug discovery, accelerating financial modeling with QMCI, tackling complex optimization problems.
But we also grounded ourselves in the reality of today's noisy, intermediate-scale quantum NISQ hardware, the diverse technologies being raced, and the massive challenge of achieving fault tolerance through quantum error correction.
And we can't forget the crucial future considerations, the proactive development of post-quantum cryptography, the ethical need to address potential bias in quantum algorithms, and the importance of bridging the potential quantum divide. We mapped out that whole dynamic ecosystem, too.
It's a complex picture, but hopefully one that feels much clearer now.
Absolutely. I feel like you our listener now have a really solid foundational grasp of this field. You're equipped to understand the headlines, the breakthroughs, and the challenges. You're genuinely well informed about the quantum revolution unfolding around us.
And as we stand here, really on the cusp of this new era, with so much potential, but also so much still uncertain, perhaps the most crucial question for all of us to ponder is this. As quantum computers inevitably become more powerful, as their revolutionary capabilities come online, how do we, as a global society, ensure that this power is developed and deployed responsibly? How do we make sure its benefits reach everyone, and not just a privileged few?
That's a deep thought to end on. Ensuring this incredible technology serves humanity equitably. Food for thought indeed as the quantum race continues. Thank you so much for joining us on the deep dive.